Okay, so today we'll be solving this problem, and like always, I hope by now you can have it memorized, but the procedure is always step 0, read the problem statement, do some type of figure summarizing the input and output. Then you need a figure. That this figure sometimes is a little bit different because that's the figure you will be using in order to write down the equation, the main equation. If you can solve at this step, you can jump directly to step 4. But if you need additional equation, you might need step 3. All right, so let's read the problem statement over here. So step 0, nitrogen at 100 psi and 300 degrees Fahrenheit in a rigid container. So we know P1 equal 100 psi, T1 300 degrees Fahrenheit is cool until its pressure is 50. So P2 equal to 50 psi, and if it's cold, that means that there is heat coming out. Determine the work done and the heat transfer during the process. Okay, so step 1 will be almost the same over here, but maybe with some little additional information. So this is our rigid container, so that means that we are dealing with a closed system. All right. In addition to that, there is heat going out. So heat going out will always be negative. If you remember the sign convention for heat in a system is always positive going in, positive coming out. All right, and we know we deal with nitrogen, so we know that if we need, we can use the ideal gas relations, or relation in this case. All right, so we go to step 2. So in order to determine the work and heat transfer, that is what is the equation we can use. We can use the first principle of thermodynamics under either form, but again, in this case, we're going to use the Q minus W equal change in the energies, and the work of the pressure then will be plus PdV. All right, so in this case, if we use that one, the work going in is negative and the work coming out should be positive. So if we use that relation, we have Q minus work equal change in internal energy. All right, so now if you look at the figure, is there any work being done? No. So now, is there any heat? Yes, heat is coming out. So this will give us that Q equal change in internal energy. And since N is a gas, we know that this will be equal to M CV dt, or delta T is the same. So this will give us that Q over M equal to CV, and delta T should be equal to what? T2 minus T1. Okay, so let us check over here. We have all the information that we need in order to solve. So we know T1 is 300 degrees Fahrenheit. Or if you want, if you use in Rankines, will be what? 300 plus 460, 760, but it's not really needed in this problem. You will see why. And now we need CV. So CV, that's a specific heat, and it is specific to each gas. So in order to find it, let's see, we go to the table A to E on page 933 to the Zengel textbook. For nitrogen, for CV, because this is constant volume, you will find that it's equal to 0.177. So from table A to E, CV, why do we use CV? Volume V1 equal V2, so it's constant volume, equal to 0.177 BTU pound mass per degree Rankine. All right. But now we don't know T2, but we know P2, P1, and T1. So here, if you want, let's call this step 3. Since we know that the nitrogen is an ideal gas, we can say that P1, V1 equal to nRT1, P2, V2 equal to nRT2. So if you just divide the top one by the lower one, you will have P1, P2, V1, V2. All this will cancel out, will be equal to T1 over T2. Now we know we are dealing with a closed system, so V1 equal V2. So this ratio here will be equal to 1. So we know P1, P2, and we know T1. So from this expression, we can find that T2 will be equal to what? T1, I move T2 to the other side, P2 over P1. Okay, so finally, I will go to the next page. Step 4. We can just combine the two equations. We have Q over M equals CV T2 minus T1. But we know that T2 is equal to T1 P2 over P1. So this will become CV T1 P2 over P1 minus T1 or Q over M will be equal to CV T1 factor of P2 over P1 minus 1. All right. So if we do the numerical application, we get Q over M will be equal to what? CV 0.177 BTU LBM Rankines. T1 we say will be equal to 760 Rankines times P2 50 over 100 minus 1. Okay, So if you do the calculation, you will get, let's first look at the units. So this has no units because the pressure, right, cancel, and we end up with BTUs over LBM as required. And the numerical value is 67.26 BTUs LB. And you see actually here, this is negative value. Okay, so why do we get a negative value? Because as we said over here on the system, if the value is coming out, so this is losing heat, the value needs to be negative.